Hello, everyone, and welcome to this exam revision webinar for Mathematics 1. My name is Siri Coletus, and it's my pleasure to be here on behalf of LSC today. So we have a 90-minute session, as you know, and what we'll be focusing on is exam-style questions, where I'm going to solve these live using my iPad, just so that you can get examples of how to structure your answers in the exam. And at the same time, it will allow us to review many of the key topics in the course. And starting then with question number 1. Here we have a system of linear equations, 3 equations here in x, y, and z. And there is some number a appearing here in this system. And we're asked to use row operations to determine the values of x, y, and z in terms of a. And so the natural place to start then would be to go straight to the augmented matrix. But since we're doing revision, let's remind ourselves of what this system looks like written in matrix form. And then we will write down the augmented matrix shortly after. So we're going to have a 3 by 3 coefficient matrix here. Then we have a vector of unknowns. And then we have the right-hand side. And so what goes into the coefficient matrix is simply the coefficients of x, y, and z. And the right-hand side is as follows. Now, if we wanted to, we could give these a name. And so now we want to start our answer by creating the augmented matrix AB, and then we'll do row operations on that. And so now we write down the coefficient matrix, and then it's nice to put a line, if you like, to separate out the right-hand side B. Now we see here that we have a so-called leading one in the first row there. And what we want to do now is to create zeros below that leading one. And that is what motivates the row operations we're going to do. Now it is useful to write down your row operations just so that you see the calculations you're doing in case you have to go back. So you see here that if we do row 2 minus 2 times row 1, well, then this 2 here will become a 0. And likewise, row 3, if we deduct row 1 from row 3, then this 1 in the third row will become a 0, which is what we want. And so we're keeping row 1 fixed. And now we're just performing the calculations here. 1 minus 2 times 1, that's minus 1. 0 minus 2 times 1, that's minus 2. And then we have 3 plus a minus 2 times, and then brackets around the 4 plus a. And that's going to give us minus 5 minus a. Moving on to row 3, we are deducting row 1 from row 3, which gives us the following result. then minus 4 minus, and then remember brackets around the 4 plus a, so we're going to get minus 8 minus a. Now we see here that convenient next step now is to make this minus 1 here into a leading one by multiplying row 2 by minus 1. So the rest stays the same. And we're just multiplying row 2 by minus 1. Okay, so now we have our second leading one. But as you know, our aim here is to have the coefficient matrix here in so-called upper triangular form, which means that we need all zeros below the main diagonal. So this minus 2 here, we would like to make into a 0. And so if we do row 3 goes to row 3 plus 2 times row 2, then we will achieve that aim. And I'm using arrows here. Remember, these matrices are not the same, so we can't use equal signs, because we are changing the equations that these correspond to as we go along. Okay, rows 1 and 2 stay precisely the same. And now we just need to add 2 times row 2 to row 3. And actually we were quite lucky here, because now we also have our final leading one in the third row. So now this matrix is in upper triangular form. We have zeros below the main diagonal, and we also have leading ones on the diagonal. And so first of all, let's appreciate that this row reduced matrix here responds also to a system of equations, but you can see now that we have changed some of the equations. The first equation, x plus y plus z equals 4 plus a, well, that's precisely the same as we started with, because we didn't do anything to row 1. But the second equation in this system here now is y plus 2z equals 5 plus a. So that's not the same as the one we had before. And our final and third equation is z equals 2 plus a. That's not the same as the third equation in our system either. But what is it that these two linear systems have in common? It is that they share the same set of solutions. So it's the same point, the exact same values of x, y, and z that all these three equations here or here respectively have in common. But by performing row operations, we have simplified the system in the sense that now we can use back substitution. The last equation, as we said, already tells us that z equals 2 plus a. Looking at the second equation, y plus 2z equals 5 plus a, well, we can make y the subject of that and say that y equals 5 plus a minus 2z, but z is 2 plus a. So let's put that in here straight away. And now we just need to perform the calculations. We get 5 minus 4, that's 1, a minus 2a, that's minus a. And finally, x equals, just rearranging now for making x the subject here, it's x equals 4 plus a minus y minus z. But we have the solutions for y and z respectively, so we substitute those in here. And then we just need to perform the calculations. And we should get that this is 1 plus a. So that's our job done. We have found the values of x, y, and z that solves this system. Do remember to check your answer, especially as you're doing a revision, but obviously ideally also in the exam. It's time depending, but at least then you can catch if you have made a numerical mistake. And what do we mean by checking our answer? Well, remember that these answers for x, y, and z, if you plug them into each of these three equations, they have to satisfy the system, right? So that's what we mean by checking our answer. So do practice that so that you get that confidence that you know how to check your answer. Now, moving on to the next question. We have a question here on Lagrange multipliers, and it says, use the method of Lagrange multipliers to find the positive values of x and y, which maximize this expression we see here, 2x over x plus 2 plus y over y plus 1, should now be subjected to the constraint that x plus y has to equal 120. So take a few seconds to think about how do we construct the Lagrangian and what is the system of equations that we need to solve. And I'm going to do it in just a moment. Okay, so the Lagrangian starts with, you write down the expression that we are maximizing or minimizing if we were minimizing. And then the convention in the course is to now write minus lambda. And then you look at the constraint equation, and then we write that in the form x plus y minus 120 equals 0. And then we write x plus y minus 120 here. So that's the Lagrangian. And what's the system that I talked about that we are solving? Also known as the first order condition. So it's all the first order partial derivatives of the Lagrangian set equal to 0. So I like to use this compact notation here where I just use x, y, and lambda as subscripts indicating the partial derivative of the Lagrangian with respect to each of these variables. And of course, in general, these partial derivatives are functions of x, y, and lambda. And this is very nice to set up in the exam. Not only does it show the examiner that you know what you are doing, but it also tells you what you need to do, right? So this is very structured. And now we just need to start partially differentiating, and then we are going to solve this simultaneous system. Now, when I look at the Lagrangian here, and I want to find the partial derivative of L with respect to x. So the first term obviously has x's in it, doesn't have any y's and lambdas. Remember, for the purposes of partial differentiation, we're now going to treat y and lambda as constants. But this one here, it's not something I say, I think I can do that in my head and just write it down. So I'm going to have to work it out. So I'm going to do that working just down here. Remember, we need to show all our working. And of course, it's not about doing mental arithmetic in maths. So why don't we just write that down here? Now I'm writing partial derivative. But you can notice here, this coincides in this case with the ordinary derivative, just because there aren't any y's or lambdas in this expression 2x over x plus 2, but that doesn't matter. We are differentiating now this with respect to x, and using the quotient rule, it is the derivative of the numerator times the denominator minus the numerator times the derivative of the denominator with respect to x, which is of course just 1, but I'm writing it for clarity here. And then we square the denominator. And you see now in the numerator, we have 2x plus 4 minus 2x. So the 2x terms there vanish, and we are left with 4 over x plus 2 all squared. So now I'm going to write that up here. Okay, and then I need to continue with this expression, differentiating partially with respect to x. Now, this term y over y plus 1, that doesn't have any x's in it, so it's treated as a constant, and so differentiated with respect to x, it is 0. And the only other term that involves an x here is minus lambda x. So differentiated with respect to x, we get minus lambda. And then we set this equal to 0. Then this is our first equation in the system. Moving on with partially differentiating with respect to y, the first term here obviously doesn't have any y's in it, and now x and lambda are treated as constants. So that will be 0. But then we have this y over y plus 1 term here. And again, I'm going to do my working here. And again, we could apply the quotient rule. So the derivative of the numerator times the denominator minus the numerator times the derivative of the denominator, and then we square the denominator. And you see again here that it's y plus 1 minus y, so it's just 1 over y plus 1 all squared. And now moving on, the only other term here that involves y is minus lambda times y. So partially differentiated with respect to y, we get minus lambda, and then we set that equal to 0. Finally, partially differentiating the Lagrangian with respect to lambda, that is easy enough to do. It's just minus and then this entire bracket here. And now, of course, this can be simplified. You can multiply both sides of this equation by -1 and rearrange to simply recover the constraint equation that we started with. And now the next step is that we would like to eliminate lambda from equations 1 and 2 so that we get an expression for x in terms of y and vice versa that we can substitute into equation 3, which will then become an equation in one variable only. I'm just going to write, since we're doing revision, write what we're doing. So looking at the first two equations then, if we send this minus lambda to the other side, we have that lambda equals 4 over x plus 2 all squared. And in the second equation, we see that sending lambda to the other side, or adding plus lambda to both sides, if you like, we have that lambda equals 1 over y plus 1 all squared. And so these two expressions for lambda can then be equated as follows. And then we just need to simplify this. Now I'm going to just directly rearrange so that I have the x's on the left here. If you take a moment to look at that, you will see that that is equivalent to the previous. And now we take square roots. And so we see that this Lagrangian function actually has two critical points. Remember, and we'll come back to this in another exercise later, what we're doing here when we solve this system of simultaneous equations is that we are effectively finding critical points of the Lagrangian. Now we have already been told that it's positive, the values of x and y which maximize this expression are positive. So we already know that we can select the positive sign. And now you see here that we have x plus 2 equals 2y plus 2. So the 2's there cancel, and we're left with that x equals 2y. And equivalently, we could have said that y equals x over 2. That's, of course, exactly the same. So, but we have what we wanted. By eliminating lambda from equations 1 and 2, we now have a relationship between x and y that we are going to substitute into equation 3 to make equation 3 an equation in only one variable. And so since I've solved for x here, I'm going to substitute x there with 2y. So let me actually write that here, that we're subbing into equation 3. And so 3y is 20, and so the value of y that maximizes the above expression subject to the constraint we have been given is 40. And now we use the expression we found above, that x equals 2y. So x equals 2 times 40. In other words, x equals 80. And if we wanted, we can write a line that these are the two values of x and y that maximize the given expression subject to the constraint that x plus y must equal 120. which you can indeed see here that 80 plus 40 is 120. Now, so far so good. Let's move on to some integration. So I have two integrals for us here, so let's focus on the first one first. Just having a look at it, just in order to just engage our revision muscles. Let's see if you can think of what method is appropriate here and how we need to approach this question. And perhaps you're thinking of partial fractions. And indeed, that's what we are going to do. Before we start integrating, we are going to express the integrand here in a different manner by using the technique of partial fractions. First thing we need to do is factorize the denominator. And so if you can spot how it factorizes, then that's fine. You can also use the formula for the solutions of quadratic equations if you can't spot it. But I've chosen so-called nice numbers here. So if we have two numbers whose product give us 12 and whose sum give us 7, then we have what we want, which you can see here. That x plus 3 times x plus 4 give us precisely that. X squared plus 4x plus 3x, that's 7x plus 3 times 4, which is 12. And then we know that the theory of partial fractions tell us that we can write this here in the following form. For some numbers a and b that we are going to find. And how do we do that? Well, we create the lowest common denominator, which is x plus 3 times x plus 4. Multiply in the numerator accordingly, here by x plus 4 and here by x plus 3, and then we compare numerators. And so now I'm just going to write that just for revision purposes, because I want it to be very clear. And actually, as you're practicing maths, it's not a bad idea to use a few words, because often people think, oh, maths is just numbers and calculations. But if you get used to writing a few words, it helps you structure your mind, I think. That's my personal opinion. So that you remember what you need to do. You're effectively giving yourself instructions. Okay, so our numerator then will have x here on the left-hand side, and then we're going to have a times x plus 4 plus b times x plus 3. And now we can choose here convenient values for x that will help us find the values of a and b. So you can see here that if we set x equals minus 3 in this equation, well, then this term here with b will vanish because it will be b times 0, and then we'll have a solution for a. And a will then multiply minus 3 plus 4, so that's just times 1. So a is minus 3. And similarly, if we set x equal minus 4 here, well, then the term with a here will vanish, and then we'll have a solution for b. And we get minus 4 equals minus b, and so b equals 4. And now we are ready to rewrite the integral and then integrate. And these are just constants, so we can take them outside if we like. Meant to write 4. And I'll give you just a few seconds to think about what the outcome of this should be. I hope you're thinking that these are len integrals. And then we add a constant of integration. Now, moving on to integral number 2. Let's take a moment to think about what method of integration you think is appropriate. What's going to help us here? We clearly can't progress as it stands. And so we're going to use integration by parts here. And now a substitution here is not strictly necessary, but so we have a linear relationship here between x and u, but for practice, let's do it. So let's let u here as a function of x be equal to x plus 1. Well, we need to replace everything here by u. So this dx also, we have to have du. So let's see what precisely we have. Is there any constant involved, or what do we get? So what's du? It's u prime x dx by definition, but u prime of x is just 1. In other words, du is just dx in this instance. And now we can write the integral entirely in terms of u. So we have len u over root u du. And I just want to point out here, u is clearly greater than 0. There is no issue with this expression here. Clearly here, x has to be greater than minus 1 for this to be well defined. So that's implicit in the question. And now we mentioned by parts. And so it's a good idea, I think, to write down the formula. Especially because we're doing revision, but certainly nothing wrong with also writing it down on your exam paper. So what's the by parts rule? So I'm aware now that I'm using different labels, and you may have seen in the course, perhaps you have seen u and v prime or v and u prime, but I've already used u for a substitution. So I'm calling this product here simply of a function f and then the derivative of some function g, right? So that's our integrand. And in my case here now, both f and g prime are functions of u. And the whole point then of the by parts rule is that we don't know how to integrate when the integrand is f g prime. And we're going to determine in a minute, of course, what is going to play the role here of f and what's going to play the role of g prime. So that's essential to being able to proceed. But the rule here tells us that this is equal to the product of fg times f prime g du. And so the whole goal, in other words, is that because we don't know how to integrate this, but we're hoping that this as an integrand, f prime g instead of fg prime, that's going to be something we can integrate. And in worst case scenario, you can apply by parts repeatedly. You can apply it, for instance, a second time if this integral here is still not exactly something that we can progress with, but we can do it one more time. And in this case, we're just going to have to do it once. But so that is the by parts rule. Perhaps we can highlight that a little bit. Okay, so as we said, now we have the rule down. We need to determine what is going to play the role of f and what's going to play the role of g prime. And what we certainly want to get rid of here is the len u, because we don't know how to integrate len u even by itself. In fact, for that, as you will have seen in the course, you actually use by parts and a trick there. So I'm definitely going to let my function f be len u. Then necessarily g prime is going to be 1 over root u. And now, because we are going to have to integrate 1 over root u in order to find the function g, I would like to write this as u to the power of minus a half. Right? 1 over u to the power of a half is the same as u to the power of minus 1/2. And that will help us when we integrate. So with this selection then, f prime is 1 over u, and g is g prime integrated. How do we integrate this? We raise the power by 1, so that becomes 1/2, and then we divide by the new power. So 1 divided by a half, 1 divided by 1 over 2 is the same as multiplying by 2. So we get 2u to the 1/2, so 2 root u in other words. And of course, it's worth mentioning that this answer is easy to check, because when we differentiate g, we have to go back to g prime. So let's differentiate this. If we have any doubt whether we have done it correctly, power comes down, 2 times a half, that's 1. And then the power is reduced by 1. And so the new power is minus a half. And so indeed, we have done it correctly. And now you'll see in the past papers and stuff, probably you're not going to see this expressly written out, but I would highly recommend that you do, unless you feel extremely confident that you can, you can do this all in your head. There's absolutely no reason to, right? Write this down so that it's clear. And then now we have apply the formula. So f times g, I'm just actually going to rearrange it as g times f. So 2 root u len u. And then The other advantage now, so now we're going to write minus and then this integral here, f prime g, and we have this all lined up here. Now, of course, you could say you could simplify this directly, but I want to show the steps very clearly here, and that's certainly preferable to making a numerical slip. So here's what we are now integrating, and of course, yes, now we need to simplify this. So 1 over u is the same as u to the power of minus 1. Well, first of all, the 2 can come outside. So 1 over u to the minus 1 times u to the half. That's just properties of powers now. That becomes, we add the powers together. So minus 1 plus 1/2, it's u to the minus a half. And you can see here, indeed, this is something we know how to integrate, right? So here, this new integrand here, we can deal with easily. Where in fact, we dealt with it before because we integrated it when we found g. So we're extra lucky here, and we can just write this down. So this is an example in action then of how something we didn't know how to integrate became quite simple. And then we add the constant of integration. And now we just want to go back to x at the end, since we did a substitution here. We do need to express everything in terms of x, and u is x plus 1. And so that is the final answer. So notice also, when it comes to what I said, the crux of the matter here is to select the functions f and g prime in order to get somewhere. But there's nothing wrong in trying something else. It's just that it may not lead us to an easier integral here. So a valid mathematical expression, but not useful if the resulting integral isn't easier than the one we started with, right? So nothing wrong in trying different things to appreciate what works and what doesn't. Now, next question. So this is a question on sequences. Looks a little long, I know, but let's just read through the information and you will see that it's quite straightforward once we have all the information down. So it says that under the new initiative in technology scheme, it's expected that there will be a new number, capital N, of new high-tech businesses starting up each month. Now, there are already capital M such businesses in existence, but it is expected that each month, 5% of all those in existence at the start of the month will fail. Find an expression in terms of M and N for the number YT of businesses in existence at the end of T months, and hence determine in terms of M and N an inequality that should be satisfied to ensure that YT will increase. So obviously we're going to deal with the first question first here. So we need an expression YT for the number of businesses in existence at the end of T months. And here it's extremely important, obviously, as always, to answer the question. So I'm going to write down here what YT is supposed to mean. And why is that important? Imagine now, for instance, if the question said, let YT be the number of business in existence at the beginning of T months, right? That's something else. The same thing, think to a question on savings accounts. It will be different if YT means how much money you have in the account at the beginning of a certain month or year, or at the end of a certain month or year, right? That makes it very different. So interest has accrued and you are saying what the balance is at the end of year 1, year 2, and year T instead of at the beginning, right? So that's why I'm emphasizing we need to see what we have been told that YT is supposed to mean. And now we want to build the pattern. So Y1 then, well, what is Y1? According to my definition above, it is the number of businesses in existence at the end of 1 month. So let's see how many those are. We were told that we already have capital M businesses in existence, but once we get to the end of the month, 5% of those in existence at the start of the month will have failed. So we are left with 95% then of the businesses that were there at the beginning of the month 1. But during the month, also, there's a number N of new high-tech businesses starting up. So by the end of month 1, we got plus N businesses. Now Y2, again, what does it mean? The number of businesses in existence at the end of 2 months. So what did we start with? If we follow the pattern above, now we started with Y1 businesses, because that's what we had at the end of month 1. They were still there at the beginning of month 2. But by the end of month 2, 5% failed. So we were left with 95% of those. But then during month 2, another N businesses started up. Now this expression, though, is not so useful to us as it stands to build the pattern, but we can replace Y1 here with the expression we found for Y1 above. So we are going to multiply this entire expression for Y1 by 0.95, and then we add N. So now we get 0.95 to the power of 2. So now we start seeing that, well, the part here including capital M, that's separate. But here there's something happening. Some geometric progression seems to be appearing here where we have a first term N and then we have a common ratio of 0.95. But let's do one more before we go to YT, just so that we are completely sure that the pattern is clear. So at the end of the 3rd month, we have all the businesses we had at the end of the 2nd month, which is Y2. 5% failed by the end of the 3rd month, so we're left with 0.95, and then we had another N new businesses. And again, now we replace this Y2 here by this entire expression we found here. And now I think it becomes clear what the pattern is. And we are going to be able to write down an expression for YT. So now we can generalize here. And how do we generalize? Well, we look at when the index was 3, the power here was 3. So that was the same. So when the index is T, this power is going to be T. And then what is this power going to be? Well, when the index was 3, this power was 1 less. And then the powers go from 2 to 1 to 0, because remember, you could see this N here as N times 0.95 to the power of 0 if you like. So 0.95 raised to the power of 0, well, that's 1. And so this here, if we wanted, we could write down this t minus 2. It will continue like that, dot, 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 all the way down to this tail here that we had above. And of course, we want to simplify. And I mentioned the word geometric progression. And here we have a sum here. Start seeing something happening here that should be familiar from the course. And so there is a formula that we can apply. But in order to apply the formula, we do need to know 3 things. We need to know the first term. Okay, that's n. We need to know the common ratio. Well, that's 0.95. And then there's one more thing that we need to know. And that is the number of terms here that we are summing. And perhaps, and that's where sometimes things get unclear, because how do we count here up to t minus 1? What is the sum? Is it t minus 1 terms? Is it t? Is it t plus 1? How many are there? So the key, one trick to do that is just to go back to, let's say, y3. So when the index was 3, how many terms were in this part involving n here? It was 1, 2, 3. In other words, we had 3 terms when the index was 3. And the same thing is the case here. Then when the index is t, here we have t terms. So you can see it's basically 1 more than the highest power, right? Because as we go upwards, this 0.95 raised to the power 1 is already the second term. So this t minus 1 power here, well, that's already term number t. So there are t terms. So let me write that down and then write down the formula. Feel free to jot it down if you remember it. And you will see in the course that there are various examples, and it's not always t terms. It can be t minus 1, it can be t plus 1. And so that's where you just need to establish that, and then you can apply the formula. So we like to call the first term little a, so that a equals n. Common ratio, we like to call it little r. So that's 0.95. And we already said it's t terms. So in terms of the notation given in the course, then the formula is a times 1 minus r to the t over 1 minus r. And of course, you can put that a in the denominator if you like, right? That's the same thing. So this is the key here. This power t here is the number of terms here that we have figured out is t. Okay, so now we apply that formula in our case. So as we said, this term with a capital M is separate. Okay, so here we have applied the above formula, but now you see that we can simplify this further because 1 minus 0.95 here in the denominator, well, that's 0.05. In other words, it's 5 over 100. And dividing by 5 over 100 is the same as multiplying by 100 over 5. And so it's the same as multiplying by 20. So let's rewrite that as 20n. We could go one step further and simplify this a little bit more in the sense of we can take 0.95 to the power of t common factor and then separate out this part. You see 20n there. It doesn't have any t in it. So we can separate that as follows. And then 0.95 to the t multiplies m, and then there's a minus sign there, minus 20n. So this here is our expression for yt. So that's part 1 done. And now we'd like to answer part 2, which is to determine the number in terms of m and n, an inequality that should be satisfied to ensure that yt will increase. Now, one way to go about that, and this will just give us now some training with inequalities and manipulating inequalities. Basically, what we're saying is that we would like for all t, yt plus 1 to be greater than yt, right? The next month should have more businesses than the previous month. And now we can use the expression we found for yt. Now yt plus 1 then will be just replacing t with t plus 1. And then we need to simplify this. Well, clearly the 20n's here. That's going to cancel. And what else can we do? Well, we can divide by 0.95 to the t here on both sides. That means that we'll be left with 0.95 here multiplying m minus 20n. And here we'll just have m minus 20n. But as we do that, I want to point out that we need to be careful when we manipulate inequalities. Because as you know, if we are dividing or multiplying by something negative, then the inequality changes sign. But 0.95 to the power of t is positive, and so the inequality does not change sign by doing that operation. Let me see what I said. I meant to say that the inequality changes direction if we multiply or divide by something negative. So the left-hand side reduces to this. And now we see that we can take n minus 20n common factor and rearrange. And then we are almost there. So we have m times m minus 20n times 0.95. If you think of now sending this whole thing to the other side, you're going to have a minus 1 time m minus 20n. And this is all greater than 0. And now we're getting somewhere, because 0.95 minus 1 is clearly something negative. But the product has to be positive in order to satisfy, for the inequality to be satisfied. In other words, we can conclude that m minus 20n must be negative as well, so that the product of these two factors is greater than 0. And now we're just wrapping up. Now we could just leave it like this, but let me make n the subject here. In other words, 20n must be greater than capital M. And if we now divide both sides by 20, we have that n must be greater than n over 20. And when it comes to checking our answer, well, at least it seems that it makes sense that in order for YT to increase, the number of new businesses must be strictly greater than 1/20th of M. In other words, than 5% of M, which is exactly the number of businesses that fail each month of those that were in existence. So somehow it seems that that makes sense. Now, moving on to the next question. So a firm is the only producer of two goods, we call them capital X and capital Y. And the demand quantities little x and y for X and Y respectively, and the corresponding prices PX and PY are related by the following equations. So here you see, again, a system of linear equations as we often encounter in the course. We're also given the firm's joint total cost function, and we have two tasks: find an expression in terms of X and Y for the profit function, and hence determine the quantities X and Y that maximize the profit. So just take a moment to think about how is the profit function defined. And that is total revenue minus total cost. And the total revenue here we work out by simply multiplying the quantity X of product X times its price. And the price will be a function of X and Y in general, plus the quantity of product Y times its price, which is also a function of X and Y, and then minus the total cost. So what we need to do here as a first step is to find PX and PY in terms of X and Y. Then we can work out the profit function. And now, as you know, with solving simultaneous systems, there are many approaches. So one thing we could do is, for example, to add equations 1 and 2. That's what I'm going to do here. Why is that useful? Well, because we're going to have minus px plus px. So the px's are going to vanish, and that means that we can make py the subject. So then that will give us, in other words, py in terms of x and y. And once we have an expression for py in terms of x and y, well, then we can substitute that in here and make px the subject, and then we'll have px in terms of x and y. And then we'll substitute those expressions in here, and we'll have the profit function. Now, there are many ways, of course, of going about it. This is one of them. And just to demonstrate above what happens if we add equations 1 and 2, well, you can just see it like this. You're adding, the px's vanish, and you get the following equation. And then we make py the subject. So that's what I'm going to do below now. And we can divide this, both sides of this equation by -3, so that the coefficient of py becomes 1, and then we make py the subject. And then we just need to be careful with the signs. We're dividing by -3 on both sides. And now we can rearrange. So that is an expression for py. And now we can substitute that into equation 1. Remember here that this equation 1 here, if we make px the subject, basically sending this minus px to the other side, if you want to see it like that, and then I'm just writing it on the left, px equals py plus 13 minus 3x. And now we're going to plug this expression for py in here, and then we'll have px in terms of x and y. And now we just pull it all together. We get 26 minus 4x minus y. And now we are ready to work out the profit function. And let me just write it down here again to be very clear. And now let me directly then multiply px by x. py by y. And then deduct the cost function which we were given in the question. And now it's a simple matter of just pulling this all together. And of course, we can put the variables in any order we like. I'm just gonna work in the order I have them. So I'll start with the x's. 26x minus 14x is 12x. Then we have minus 4x squared. There aren't any other terms involving x squared. Then we have minus xy minus xy. Then in terms of y, we have 13y minus 7y. And finally, there's a minus y squared. So that is the expression for the profit function. And now we want to determine the quantities of x and y that maximize the profit. So have a little think about how you would start on that. Now, the first thing we need to do is to find any critical points of the profit function. And remember that when we solved the Lagrangian earlier, we used precisely those conditions. So for a multivariate function, any critical points satisfy the so-called first order conditions. And remember that these are the first order partial derivatives of the profit function set equal to 0. So yet another simultaneous system of equations that we need to solve. And so the first thing we do then is to find these partial derivatives. Now, partially differentiating the profit function with respect to x, remember that we treat y as a constant. So take a little head start and see if you can write down or see what the result is going to be. So the 12x term is going to give us 12 differentiated with respect to x. The minus 4x squared term, well, the power comes down and the power is reduced by 1. So we get minus 8x. Now the minus 2xy term, remember that we treat y as a constant. And so differentiated with respect to x, we get minus 2y. And the rest of the expression for the profit function involves only y, and so those are treated as constants and so differentiated with respect to x now. That gives us 0. Similarly, now we differentiate the profit function partially with respect to y. So now we treat x as a constant. And so we only need to look at the last 3 terms. Okay. And now we just write those into this simultaneous system, where we set these equations equal to 0. I'm just going to order them the same way here. That can be especially useful if you are adding or subtracting equations. I would just have the constants and the x's and the y's lined up. So notice here, like we said, yet another system of simultaneous equations, no different from what we solved up here. So there are many possible ways of solving this. For instance, you can see that there we have this minus 2y here in both equations. So if we do the first equation minus the second equation, you're going to get minus 2y minus minus, that's plus 2y. The y's will vanish, and you can solve for x, and then you can substitute that solution for x back into one of the other equations. That's one way to do it. Just practice different ways. I'm just going to solve it in a different way now, where I substitute into something from the first equation into the second equation. So I can write the first equation like this. 2y is 12 minus 8x, and then I can plug that into the second equation. And we have minus 2x plus 8x, that's 6x. 6 minus 12, that's minus 6, and that's equal to 0. We can send this minus 6 to the other side. So 6x equals 6. So x equals 1. And then we go back to the first equation. First, let's notice, perhaps it's easier now if since we didn't make y the subject the first time, well, y is a half times 12 minus 8x. And now we substitute this in. So y equals 2. So this profit function only has one critical point, which happens when x equals 1 and y equals 2. But is it a maximum is the question. And there we need to move on to the Hessian, and now we need to calculate the second order partial derivatives. So now we take the first order partial derivative of pi with respect to x, and we partially differentiate with respect to x one more time. And we get -8. Then we take the partial derivative of pi with respect to x, and now we partially differentiate it with respect to y. And that's -2. I hope you agree. And just to mention that this agrees with the partial derivative of y, now again partially differentiated with respect to x. And finally, we take the partial derivative of pi with respect to y, and we partially differentiate again with respect to y. And you see that there's only one term there involving y, so we get -2. And now we work out the Hessian. Which is pi xx times pi yy minus pi xy all squared. So we get -8 times -2 minus -2 all squared. And so that's 12. But what we're mostly interested in is that it's positive. Recall that if the Hessian is negative, then it's a saddle point. If you have the Hessian negative at the critical point. Now here it's positive. In fact, it's positive for all x and y. And then we need to also work out, we already worked it out, but we need to state it, that pi xx is negative. And so positive Hessian together with pi xx being negative, that means that indeed the profit is maximized when x equals 1 and y equals 2. It is in fact a global maximum for the profit function. Okay, that brings us to the end of this presentation. So I hope that's been useful, seeing how we write our answers and also to revise some of the key topics from the course. So remember that in the exam you can answer questions in any order, but if you're uploading your paper, then do organize your questions in ascending order before you upload. Also, just practice as you're revising, getting the overview of the different topics. Be accurate with your calculations, nothing wrong with drawing a line through your calculations if something has gone astray, and starting again. And you will see that as you get closer to the exam that you will reach top form. So with that, I wish you the best of luck, and I hope you have enjoyed the course. It's been my pleasure to be here with you today, and wish you all the best with the rest of your studies with us here at the University of London with LSE, and have a great day, everyone.